Good morning, dear students. Uh, we are we are studying or we are learning Water Resource Engineering Subject 1, Unit 3, Runoff, and the subtopic is the stream gauge. So, guys, here stream gauging. It is a stream gauging means actually it is a technique used to measure the discharge or the volume of water moving through a channel per unit time of a stream. The height of water in the stream channel, known as a stage or gauge height, can be used to determine the discharge in a stream. And the stream flow, representing the runoff phase of the hydrological cycle, is the most important basic data for hydrology studies. Stream flow is the only part of hydrological cycle that can be measured accurately. Runoff from a catchment can be determined by measuring the discharge of the stream draining it, but necessity of a discharge measurement. By measuring the discharge in the river, the irrigation water can be distributed uniformly. By measuring flow in rivers, flood warning can be issued. By measuring the discharge in river, the irrigation water can be distributed uniformly and can be issued. Guys, here, by measuring flow in canal, quantity of losses can be known. The quantity of water flowing in the river helps for future research and site selection for a stream gauge. Site selection for a stream gauge site. Here, guys, but before doing a site selected on stream for the purpose of measuring discharge in the stream continuously is known as either a stream gauging station or a hydrometric station. The stage discharge relation at the stream gauging station is defined by the complex interaction of the channel characteristics, including cross-sectional areas, shape, slope, and roughness. The combination of these effects is called the control. A control is said to be a permanent control if the stage discharge relationship which it defines does not change with time. On the contrary, it is known as either an impermanent control or a shifting control. The shifting control may be due to the effects of changing channel, store and silt in alluvial streams. Backwater rapidly changing stage in the stream, unsteady flow conditions, variable channel storage, aquatic vegetation. After a gauging station has been established and sufficient discharge measurements have been made to determine the stage discharge relation, it becomes necessary to make additional measurements at various stages from time to time to know just how rapidly or how slowly the control is changing. A control should never be assumed permanent until it has been proved so by a number of measurements made after the passage of floods. There are four criteria in selecting a site for establishing a stream gauging station. They are accessibility, adequacy, stability, and permanency. The station should be accessible under all conditions, particularly during floods. The station should be able to cover the full range of discharge which may occur. The stage discharge relation at the site should change with time as little as possible. This aspect is very important both from the standpoint of cost of operation and accuracy of stream flow computation. These stations should never be located upstream of a junction with another stream near enough to be affected by backwater from that stream. It should also not be located within the influence of backwater from any project. The station should be so situated that the installation is almost permanent and is not likely to be distributed. One of the most important feature of streamflow record is its unbroken length. Also, it should be located above points of flow diversion. Guys, the bed and banks of the stream should be firm and stable so as to ensure consistency of area discharge relationship. The bed and bank should be free from vegetal growth, boulders, or other obstructions like bridge. There should be no larger overflow section at third stage. To ensure good consistency between stage and discharge, there should be a good control section for downstream of the gauging side. The section should be straight and uniform for a length of about 10 to 20 times the width of the stream. The stream gauge station should be easily accessible. Here are conventional methods and advanced techniques, direct and indirect. In a conventional methods, direct velocity area methods using current meter, velocity area methods by using flows, by dilution methods, indirect slope area method, by stage discharge relations, measurement by hydraulic structures. Advanced techniques, moving boat method, ultrasonic acoustic method, and electromagnetic method. Classification of methods of discharge measurement. Velocity area method. Discharge is the product of cross-sectional area and velocity of water, where Q is equal to discharge and A is the cross-section of flow. Velocity of flow at a cross-section varies. It is not enough to measure the velocity at a single point. Based on accuracy required, width of the stream is divided into a number of vertical portions. In each portion, velocity is measured at one or more points along the depth to get a representative velocity. This is the velocity area method, water level at the stream bed, schematic sketch for a velocity area station. The velocity area methods. The area of the individual portion can be easily calculated if the bed profile and stage are known. The velocity may be measured by conventional method or by an advanced procedure. And discharge measurement using artificial structures. If the physical and hydraulic conditions at the site permit, a fixed undeformable structure may be constructed to measure river flow. A number of hydraulic structures are used to measure closed infield conditions, whereas they are used to control upstream water level or for measuring discharge or for both. They produce a critical relationship between stage and discharge by obstructing channel flow. Varies have a defined cross section and hence the computation of discharge is simple. The size and cost of the structures increase as the size of the river increases. Site requirements consist of reasonably straight approach, channel which should be free of excessive sedimentation, weeds and other aquatic growth. The structure should be rigid, watertight, normal to the flow direction, and should be capable of passing high flows without any damage to its body. The stage discharge relation at the site depends on the geometrical characteristics of such a structure. This is the various where uh, plums. A plum is a flow measuring structure formed by a construction in a channel. The construction can be either a narrowing section of the channel or a narrowing section in combination with a hump in the inward. A unique stage discharge relationship exists independent of the downstream conditions. For a rectangular plum, the discharge of an ideal fluid is expressed as Q is equal to 2 by 3 to the power of 3 by 2 square root GBVH to the power of 3 by 2. Here H represents the upstream energy and B is the typical with the dimension for the particular cross section shape of the plums. By introducing suitable coefficients, this equation can be generalized to the following form. A CV is equal to coefficient to take into the account the velocity rate in the approach channels, and CS is equal to the coefficient to take account of the cross section shape of the flux. C is equal to coefficient for energy loss, and H depth of water upstream of the flow measured relative to the inward level of the throat. Dilution techniques. Two dilution techniques are the steady feed method and the instantaneous point source time indigenous method. For steady feed method, a solution of tracer material with concentration C1 is injected at the constant injection rate QT. Dilution technique. After QT injection, concentration sketch the reach and concentration time curve measured at x2 time. Dilution techniques. The tracer disperses laterally into the flow and tracer concentration distribution is similar to as shown in figure. At some point x2 downstream, where the tracer material is approximately uniformly mixed, the flow is sampled continuously. Dilution technique. If the tracer mixture has a property similar to the water, so that there are no density gradients, vertical mixing is very rapid due to turbulence of the flow. Theoretically, complete lateral mixing occurs at X, but practically it occurs between 20 to 100 times the channel width. By instantaneous injection method, a quantity of tracer is injected instantaneously at section X and time t is 18 hours. The cloud of tracer disappears laterally and longitudinally as it moves downstream. This is the dilution techniques. Dye cloud disappearing downstream and concentration at x1 and concentration at x2. At the section x2, where the tracer is completely mixed literally, the flow is sampled continuously. From the conservations of mass, in which Q is nearly constant to a sampling period. The common tracers used as salt solutions, radioactive tracer are detected by its uh, scintillation detectors, fluorescent dyes with the fluorometers. Advantages of dilution method, they condensed in closed conduits such as pen stocks, reverse pipelines, where current meter measurements are difficult and they are fast and accurate. Disadvantages: expensive for measuring large shape, special equipment is required for the measurement of concentration. Velocity measurement by floats. A float is a distinguishable article that floats on the water surface, such as a wooden log, a plastic bottle partly filled with water, or branch of a tree. Surface or near surface floats are used for stream flow measurement, which are wooden cylindrical rods of nearly 0.5 meter length. Velocity measurement by floats. They are shaped, they are shaped such that they float nearly vertically with one third of the length protruding above the water surface. The floats are painted in bright colors for easy identification in muddy or turbulent water. For a float For a plot measurement, two cross sections sufficiently far apart on a straight reach of river are selected. The upstream and the downstream cross sections should be sufficiently far apart for accurate assessment of flow travel time, 3 to 5 times the width of the river, or a minimum of 20 seconds travel time. Both the cross sections should be clearly marked by placing markers so that the exact time when the flood crosses the cross section can be identified. The upstream channel cross section should be divided into a number, preferably an odd number, of equal segments as practically feasible in which the uploads will be placed. And observer each is positioned at upstream and downstream ends of the reach such that they are visible to each other. The downstream observer acts as timekeeper and carries a stopwatch. Floats may be tossed from a bridge or cableway. If there is no such facility, then they can be thrown in the water from the riverbank. When the float crosses the upstream cross section, the upstream observer gives a signal to the downstream observer who notes the time taken by the float to cover the distance. The velocity of the float is equal to the distance between the two cross sections divided by the time taken by the float to cover this distance. The mean velocity in the vertical is determined as the float velocity multiplied by a coefficient which varies between 0.80 and 0.85. This coefficient depends on the shape of the velocity profile of the river and the depth of immersion of the float. 522. It is used for velocity measurements in order to calculate discharge in laboratory plums or very small streams. It is not recommended for rivers because it is very difficult to support it when channel is very wide and deep. The heat generated by Picture tube in open channel is typically very small due to very low velocities. Thus, discharge cannot be measured accurately. Picture tube. Formula for velocity computation is V is equal to GH to the power of half, where H is equal to water height in tube above surface of water. Current meter. It is used to measure It is used to measure velocity at a point in the flow cross section. Accurate measurements of the velocity profile of the stream cross section are made by current meters. Working of current meters. It consists essentially of a rotating element which rotates due to the reaction of the stream current with an angular velocity proportional to the stream velocity. The angular velocity acquired by the rotor is proportional to the velocity of water. By placing a current meter at a point in a stream and counting the number of revolutions of the rotor during the time interval, the velocity of water at that point is determined. Current meter. There are two main types of current meters: vertical axis meters. Here, stabilizing in host electrical connection, counting mechanism, cup assembly, 6 cups on a vertical axis, and sounding weight. Vertical axis meters. These instruments consist of a series of conical cups mounted around a vertical axis. The cups rotate in a horizontal plane and a cam attached to the vertical axis spindle records generated signals proportional to the revolutions of the cups assembly. The normal range of velocities is from 0.15 to 4.0 meter per second. The accuracy of these instruments is about 1.5% at the threshold value and improves to about 0.3 at speeds in excess of 1.0 meter per second. These have the disadvantage that they cannot be used in the situations where there are appreciable vertical components of velocities. Current meters, horizontal axis meters, posting and electrical connection, propeller, and fit for stabilization and sounding weight. Horizontal axis meters. It consists of a propeller mounted at the end of horizontal shaft. These come in a wide variety of size with propeller diameters in the range of 6 to 12 centimeters and can register velocities in the range of 0.15 to 4.4 meters per second. Horizontal axis method. These methods are fairly rugged and are not affected by oblique flows of as much as 15 degrees. The accuracy of the instrument is about 1% at the threshold value and is about 0.25% at a velocity of 0.3 meters per second and above. The number of rotations are measured and correlated to velocity using the formula V is equal A plus B and where n is the rotation of the propeller, revolutions per second, RPS. A and B are coefficients determined by calibration in an experimental plot. These constants differ from one current meter to the other as a result of manufacturing variations as well as change with the time due to wear and tear. Therefore, each current meter should be recalibrated periodically. Rating of the current meter. Considering the velocity profile with the depth, average value of velocity can be obtained at 0.6 of the depth. That is, V is equal average velocity is at about 0.60. An alternative of using the 0.60 velocity is to take 0.2 and 0.8 velocities and obtain the averages. The latter method is more accurate, but in a shallow cross section, the velocity at 0.2 T may be difficult to measure, so use a signal value at 0.60. Rating of the current method. Velocity and propel rotation, surface velocity and average velocity. Measurement of area of flow. Measurement of it. Pivot point method. This method is based on the principle of similar triangles. X and X are 2 points fixed on the cross-section line on the bank of the channel. Here, 240 meters, 300 meters, and the provided line. Here, river bank and the selection line. From point X, a pivot line is erected at the right angles to cross-section X. The length of the pivot line should be about half the width of the channel or 300 meter, whichever is more. Other extremity of the pivot line is called a pivot point marked P in at 1.5 length of the pivot line. From the pivot point, a direction line DD1 is drawn at right angles to pivot line. The direction line DD1 is divided in shootable parts of the equal lengths by points D1, D2, D3, and D2. Let the length of each part be 3 meters. Then, from similar triangles PD1, 2, and PS1, S2, the length of S1, S2 is 5 meters. The length of D1, D2 since PX is 5 times PD square. The length of each strips S1, S2, S2, S3 is 15 meters. The points EDC can be located on the cross-sections line very accurately with the help of a theodolite placed at P. When the gauge site is to be made permanent, the points D1, D2, EDC on the direction line, points and on the cross-section line, and the pivot point should be constructed with masonry in the form of blocks with a hole in the center to fix a flange exactly on the point. Measurement of depth, sounding rod. It is a wooden rod 5 to 8 centimeters in diameter with markings on it. A bamboo pole may also be used as a sounding rod. Many times a flat iron of 5 centimeters into 0.6 centimeter size may also be used for the purpose. Measurement of area of flow. The graduations are generally in tenth of a meter. To prevent sinking of rod and to achieve accuracy in measurement, the rod is provided with a flat base plate. The base plate is in the form of an iron disc 10 to 15 centimeter diameter attached to the lower end of the rod. So measurement of area of flow echo sounder. It is based on an electrical principle. It consists in transmitting a sound impulse by a transmitter from the surface of water level to the bed of the river. When the sound waves reflect back into the form of an echo, they are arrested by a receiver. There is an automatic arrangement for plotting the time of transmission and the time of reception. The velocity of sound in water is known as 1470 meters per second. From this fact, the depth of water is automatically computed. This method is of very common use on ships for observing depths. It can also be used successfully at rivers. Okay, guys, thank you. I will see you again in our next class.